Soil has many properties. One of the most important is the ability to hold on to water and the rate at which water passes through soils. So as we start to talk about soil properties and ecosystem functioning, one of the most important ones that we're going to talk about, and the first, is really the interactions between soils and water. Now the authors state that spatial and temporal variations in soil development generate large variation in soil properties. One of the most important soil properties is going to be soil texture. When we begin to quantify differences among soils, one of the things that we look at is soil texture. What soil texture is a classification of soils based on the distribution of particle sizes. So here we have 4 different classes of particles based on their size. Anything greater than 2 millimeters is considered rocks or gravel. And then we have sand, silt, and clay, which differ also in their size. Sands go from anywhere from 0.05 to 2 millimeters in diameter. Silts an order of magnitude lower than that. And then clays are things less than 0.002 millimeters, which is very, very small particle size. For the major soil textural classes, we tend to take a look at the concentrations or the proportions of clays, silts, and sands. So in the center, when you have relatively equal amounts, let me back up a second. Here on this x-axis is percent sand. And again, we're going to take a look at 3 axes at the same time because they all add up to 1, or at least 100% in this case. So the percent sand is here on the x-axis, or at least on the lower axis of the triangle. And a soil that has 0% sand is going to be over here, and a soil that has 100% sand is on this side. On this side of the triangle is percent clay. You have soils that have no clay all the way up to 100% clay. And then percent silt, 0 to 100. So a soil that's almost all sand, 100% sand, 90% sand, and only a few percent of silt. So we're going to follow this number down here. Here's the 10% silt line. So if we're at 90% sand and 10% silt, or in this case 5 and 5, 5% clay, 5% silt, that's a very sandy soil. In contrast, on this side, when it's almost 100% silt, it's a silty soil. And then clayey soils essentially have, as you can see here, somewhere on the order of 60% clay or more. And then we have different combinations of silt, clay, and sand. In the middle is what we call a clay loam, when you have relatively equivalent amounts of sand, silt, and clay. And then loams are here, and other things like sandy clays or sandy loams that are intermediate between 2 other types of soils. So we can go through a soil, we can classify the particle size distribution or quantify that and figure out if a soil is clayey, sandy, or silty, or somewhere in the middle such as a clay loam or even a silt loam. Now the reason that we do that is that there are different properties of sands, silts, and clays. And clays, for example, have a very high surface area. Clay particles have somewhere on the order of 10,000 times greater surface area than the same weight of medium-sized sand particles. And so if you have a lot more clay than you do sand, you're going to have a lot more surface area in that soil. And with greater amounts of clay and greater amounts of surface area, that means you have a greater potential for surface charge and a greater amount of cation exchange capacity than the equivalent mass of sand would. Now the authors also show the general relationship between particle size and the kinds of minerals that are present. And essentially in a very sandy soil, you tend to have a lot of quartz minerals and then some primary silicate minerals. And by the time you're down to a very clayey soil, most of those are secondary silicate minerals. And so this is also a weathering process, is that you start with the primary minerals, and then as they become physically and chemically weathered, the particle size becomes smaller and smaller and smaller. As we go down through a typical soil profile, the distribution of these sand, silts, and clays often change. So this would be for a silty loam, and it's put forward as being somewhat representative because some of these proportions change as you go down in depth. So for example, on the y-axis here is depth, and so think about this as going down through the soil profile, and the amount of organic material, which is different than these other textural classes, is highest in the shallower soils and then declines with depth. And then you can see is that as you go down in depth, you tend to have a lot more clay that's there. And then these shallower soils have a lot more macropores and it becomes more dense as you go down. And again, the macropores are going to be the spaces in between the larger chunks of soil, and the micropores are just smaller spaces in between. You can see a little bit here of just thinking about differences in aggregates and some of the other soil structure that occurs, that you can have relatively chunky soil and relatively fine-grained soil, and these are going to differ in proportion and give you differences in how much space is in between those particles too. Now, as far as water is concerned, that when we quantify the ability of soils to hold on to water, we often talk about field capacity. And what field capacity is the ability of soils to hold on to water and how much water they can hold before it's lost. So in a saturated soil, you have all of these pores that are filled with water, and water is going to drain freely. And then in a field capacity, not all the pores are filled with water. And you take a soil, fill it up with water, and then after all of the water that drains out freely is gone, the amount of water that's held on by the soil is considered the field capacity. And then often soils are going to be below field capacity because of evaporation and transpiration, for example. So we're going to separate between two different types of flows. The first is saturated flow. And again, if you have your soil and then you add water to it, saturated soil happens because for your particles that are here, there's enough water in there that gravity alone is able to pull that water through the soil. And that's a saturated flow. So it's the amount of flow that you get when the soil itself is saturated with water. Unsaturated flow happens when you have a soil and you have your soil particles in there, but the soil is not saturated with water. So there's some water in there and it's going to form films. I should have used two different colors on this one. Let's use red as our soil particles and blue as your water. Now, if a soil is unsaturated, you're not going to get saturated flow. Gravity is not going to pull hard enough on this water to pull it off of the soil particles. But if you have differences in water potential, for example, that's enough to pull water off of there. It doesn't happen via gravity, but it happens because of differences in water potential. Sometimes that goes downwards, sometimes it's upwards, sometimes it's to the side. So you still can have flow even though soils are not necessarily saturated. Now, if we have to quantify field capacity, for example, it's a pretty simple calculation. And all we want to know is for a soil, if you were to take a dry soil and weigh it, that would be the mass of the soil. And then you add the water. And again, I should make those red, just to say that the soil particles. And then you add water. And initially, this is going to be filled with water, and you're going to get saturated flow out the bottom. But once that saturated flow stops, then you're at field capacity. And if you can determine the mass of the water that's in that soil such that there's no more saturated flow, this mass of water becomes the numerator. And this ratio is your field capacity. And in organic soils, for example, you can have a ratio of 300%. So somewhere on the order of 3 grams of water per gram of soil. But in other soils that are really sandy, for example, your field capacity might only be 20%. So this would be an organic soil, and this would be a sandy soil. So in a sandy soil, because there's not a lot of surface area there, and you have relatively big chunks, there's just not a lot of ability to hold on to that water. So really you would take somewhere on the order of 10 grams of soil, and you might only be able to hold 2 grams of water. And the field capacity of that soil might only be 20%. So you could see that there would be a lot of differences in the ability of those soils to hold on to water and then supply water to plants eventually for a given amount of precipitation.